all right. He's mad at me because I blame him for everything. We're going to move the 3x squared over here. That will give me 4x squared. And I'm going to move the 5 over here, and that will give me 15. What am I going to do? Can you see what I'm going to do here? I divided both sides by 4. Since there's no x term like there was in the last problem, I could get it set equal to 0. I could use the quadratic formula, but it seems easier if I want to get x by itself to just take the square root of both sides. The only thing about that is I have to remember that when I square root this, it's plus or minus. When you take the square root of both sides, it's plus or minus over here on the right. So that's the square root of 15 over the square root of 4, which is 2. And there's the answer to the question. So if you are busy doing your 1-1 assignments, which you should be, it's full of problems that look like this. Weird, random equations to solve. Now, section 1-2 is where the meat of the chapter is. There's a lot of important stuff in here. The very first question you have to be able to answer is this thing a function? So looking at those pictures, can anybody remember how we determine if things are functions or not? Anybody remember how we do that?
Is there anything about a variable in the denominator?
Robbie? It has to do with crossing, but not necessarily the origin. There's something called the vertical line test.
Oh, yeah.
So what we do is we look at our picture, and you don't have to redraw it. You can just use the one that's on there. And you think about drawing a bunch of vertical lines down through that picture. How many times does each vertical line hit the picture? Once. If it only hits once, it's a function. Do you remember that? Now that I've said it, it's called the vertical line test. Vertical line test. Now look at B. Okay, now I'm going to pass vertical lines down through it. Now what happens?
Twice.
It hits twice. If it hits more than once, it is not a function. Got it? How about C then? Do C. Function or not?
Yes.
Yes, it is. That is indeed a function. Good work. D.
No.
No. If you draw a vertical line down through, it crosses more than once. How about E?
Yes.
Yes. How about F?
No.
No. Everybody got it?
Yeah.
Okay. Number 2. Domain. What do you think of when I say the word domain? Okay, you think of range, the counterpart of domain. So let's back up. Let's remind ourselves that a function is a set of ordered pairs in which no x values repeat. Does that sound familiar to you? It's why the vertical line test works. Both of these points have the same x coordinate. This might be the point 1, 2, and this is the point 1, -2. X's are repeated, so it's not a function. In a function, no x's can repeat. So you've got this set of ordered pairs. It's a set of ordered pairs. And none of the x's can repeat. Now, can the y's repeat?
Yes.
Yep, not a problem. None of the x's repeat. All of those x's together, so the set 2, 3, and -6, that set of numbers is called the domain. The domain is your x's. Functions are input-output machines. You put in an x value, you get out a y value. The inputs are the domain, the x's. The range, guess what that is? If the domain is the x's, the range is the y's. And if we have a repeater, we don't list it twice. In your set, you only have to list it once. Okay? Now, the next set of problems on your page say find the domain of the following. Now, it is easy if they're written out like this. But in number 2 here, or 3 or whatever, 2, they are all equations. So here are the rules for domain. You have got to know these rules. They're very simple. No zeros in the denominator. In other words, the denominator cannot be 0. You already know that. You're going to buy a Math League t-shirt that says that. It's really cool, 4-screen with gold lettering. I know you all want one.
Long sleeve.
Long sleeve or short sleeve, you get an option.
They're 10, right?
$10 for the short sleeve, $15 for the long sleeve. And then the other rule is whatever is under the radical, if you have a radical, whatever is under the radical must be greater than or equal to 0. So the denominator can't be 0, and whatever is under the radical must be greater than or equal to 0. Those are the 2 main things that are going to cause us trouble. So I want you to look at problem 2a. Is there a denominator in 2a? No. Is there a radical in 2a? No. So therefore, the domain for 2a is all real numbers. That's the symbol for all real numbers. Or you can write all real numbers. Now listen to me. These are the problems with domain. If you don't have a denominator and you don't have a radical, then you don't have a problem. And your domain is all real numbers. Everything. Now look at B. What do I have in B? A radical. Beep, 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 beep. Here go my domain radar. What do I know about radicals? Whatever is underneath has to be greater than or equal to 0. So x plus 5 has to be greater than or equal to 0. The rule says whatever is under there must be greater than or equal to 0. So what do I know about my domain? It's all the x's greater than or equal to -5. For number 2a, B, for B, your domain is all the x's greater than or equal to -5. I'm getting all worked up here talking about domain. Okay. Robbie.
How do you determine
What?
How do you determine if it's a radical?
This is the problem has a radical sign in it. Are you looking at 2b? All right. This is a radical sign. If it has that symbol in it, that's a radical. We don't want that to be, whatever's under it has to be greater than or equal to 0 every time. Paul?
So what are you writing as the answer? Radical?
You're writing as the answer either this is the way it comes out when you solve it. If you want to do it mathematically, you'll say -5 to infinity. That's your interval notation, and I don't care which way you do it, okay? This is like the real way, but if you just solve that equation, this is what it comes out to be.
So you think either way on it?
Yep, yep. Unless the directions specifically say, sometimes in your book it specifically says, use interval notation. Okay, now, let's look at C. Do I have a denominator? Beep, 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 there go the domain radar. What do I know about denominators? The denominator cannot equal zero. So x plus 5 cannot equal 0. Which means x cannot equal, subtract it over, -5. So what is your domain then? Everything except -5. You may write it this way, or if you're feeling particularly mathematical, you can write it this way. But this is perfectly fine with me. That tells me, okay, I can have everything except -5. We all right with that? Now we're on D. I'm going to leave my rules up here. We have to constantly refer to our rules. We got to get them learned. Remember, my domain is going to be all real numbers unless I have a denominator or a radical. What do I have in this problem? A denominator. What do I know about denominators? They cannot equal 0. So 4x minus 1 cannot equal 0. Right? Which means 4x cannot equal 1 and x cannot equal 1/4. This is your domain. That means every number except 1/4.
So we only look at the denominator?
Yes. Quincy, domain. If the question involves domain, we're looking for denominators and we're looking for radical signs.
Okay.
That's it.
I'm glad I just picked up on that.
At least you got it now, man.
All right, now we're looking at E. E is a trick question.
Trick question.
Do I have a radical? No. Do I have a denominator?
Yes.
Yes. So the denominator cannot equal 0. Now, tell me why this is a trick question. Well, because it's squared, something is going to happen here.
You're gonna put in a row.
Well, yeah, but not every, you're right, I am. But not every squared is going to cause me a problem. This one causes me a problem because when I subtract and divide and take my square root, I'm going to get an imaginary answer. The other thing about domain is we're going to keep it real. We're not going imaginary. So this doesn't count, it's imaginary, which means my domain is all real numbers. What I thought might be a problem turned out not to be a problem because it took me into the imaginary realm. So that means it's not a problem. I'm keeping everything real. I'm not considering imaginaries. So this domain is all real numbers. This says x can't be, I didn't put cannot be, it can't be imaginary. Yeah, you're right, it can't. it can be all real numbers. It can't be imaginary. It's a little tricky. Not for us though, we're good. F. Okay, question is about domain. Every time somebody asks me about the domain, two things pop into my head. Is there a fraction? Is there a radical? What have I got in this problem? A fraction. So I know my denominator cannot be 0. Right? Which means x cannot be 0. So what's my domain? All reals except 0. Now, you can write it this way. You can write it the real math way.
Will you make us write it that way on the test?
Probably not.
Wait, so E is just all real numbers, like you don't have to say like not.
Yeah, E is all real numbers. Because what it was going to not be was imaginary. And I'm real. I'm not talking about imaginaries here.
She's a real.
Right?
Real.
I am real. Yes, I am. Okay.
She's a real
Now, I'll do G over here, so we leave that one up for another day. All right. Now look at G. Does it have a radical?
No.
No. But it does have a denominator. Now, that means that x squared minus 9 cannot be 0. Now, what do you think we're going to do with x squared minus 9? Well, we could say x squared isn't 9, move the 9 over to the other side, and square root both sides. If you do that though, don't forget it's plus or minus 3. Some of you at this point, instead of doing that, what else could you have done? Difference of squares. X plus 3, x minus 3. Which means x plus 3 can't be 0. X minus 3 can't be 0. So x can't be negative 3 or x can't be 3. On board? So that one has 2 cannot be's for its domain. Oh my gosh. Look at H. What's the deal with H, you guys? It has major issues because not only does it have a radical, but it also has a denominator. Okay? Now, what do I know? Colleen, you all right back there? You writing all this good stuff down? Good. All right, what do I know about radicals? When I see that radical sign, what do I know about radicals? Whatever is under it is greater than or equal to 0. So 5 plus x is greater than or equal to 0. Which means x is greater than or equal to negative 5. So that takes care of the first problem. But this one also has a denominator. And what do I know about denominators? They can't be 0. So x minus 2 cannot be 0, which means x cannot be 2. So your answer has 2 parts to it. You're telling me, okay, your domain can be any number bigger than or equal to negative 5 except 2. So if you graph that, on the number line, if you did, I'm not telling you I'm gonna make you graph it, but if you did, you'd have a solid dot at -5 and you'd shade this way. But at 2, you'd have to open it up and put an open dot. It like skips over 2. That's what your domain would look like if you drew a picture of it. Both of these are part of the answer because you had both problems, radical and denominator. Problem I.
Oh, wait.
Which problem do I have in problem I? I have a radical. What do I know about radicals?
It must be greater than
Whatever is underneath has to be greater than or equal to 0. So if I subtract 2 and divide by a negative, my domain is less than or equal to 2.
It's bigger than 0.
Whose man?
It's less than
All of your rules that you learned about how to solve still holds true. When I divide by a negative, I have to remember to switch the sign. Okay? One more. C of x. Square root of 3x plus 1. I have a radical. I know that whatever is under the radical has to be greater than or equal to 0. So 3x, it's, sorry, get irritated. You won't like me when I'm irritated. X is greater than or equal to -1/3. That's my domain. Now I would suggest that if you have not already written this down somewhere, these two things in the boxes, that you get it written down. I'm getting ready to erase it. In the box, just write down what's in the box. And we use this anytime the question involves domain. Everybody okay? All right, well, I told you today we were going to do some heavy-duty stuff. That is a huge idea. Not hard to remember, but a huge idea. Another huge idea is the notion of asymptotes. Does anybody know what the word, or what it means to be an asymptote? I think you might have talked about it last year, maybe not. You remember that word?
When you have like that graph go like this, it's where it doesn't cross.
Exactly. So I was thinking when you studied them last year, you may have studied them in terms of a hyperbola. So one of our BFFs, one of our basic family of functions, our 12 basic curves, has 2 asymptotes. Asymptotes are like the guidelines for the curve. The curve, as you move off the page, the curve gets closer and closer and closer to it. That's called an asymptote. This one is a horizontal asymptote. And when we say the word asymptote, notice there's no P at the end. You'll hear people say asymptote. Only like say that. It's an asymptote. This one is a vertical asymptote. Okay, now it's time for a quick story. See this black shirt hanging up here on the wall that says "Got Math"?
Yeah.
Okay, so let's see, it would have been like 2007, 8, 9, somewhere in that area, trying to figure out a math league shirt. and we found one we just totally loved. That one right there. Thought it was awesome. On the front it says, got math. On the back it says, you bet your asymptotes. Okay, so we think it's so awesome. Administration shot it down. So I was teaching IB math at the time, and so we were taking our final exam time, and in they all come, and they're just giggling like crazy. And they're carrying this bag, and they had underground. They took off their uniform shirts, and underneath they all had on that T-shirt, and they bought me one.
That's
So
awesome.
we all had our little IB, you bet your asymptote shirts on for one day, and then of course we had to put them away. And of course I'm saying this in front of the president's kid. Actually, I don't display the back of it, so but that's what the back says. I thought that was so cute. I loved it, but they wouldn't let us do it. Okay. All right. So what are we doing with asymptotes? What are we doing with it? Well. Oh shoot, I think I just said all that on video too. If I'm not here Tuesday, you will know why.
We gotta do some editing.
Alright, so we're going to find the vertical asymptotes and graph them. Now remember, nothing big about graphing vertical asymptotes, they're just vertical lines. When we sketch them, we do dash them, like a dashed line. So we need to know where to put the vertical asymptote. Well, I'm going to tell you where you put it. The vertical asymptote denominator equals 0. Now, you're saying to me, what, denominator equals 0? No way, Mrs. Ford. Well, that's where we put the asymptote because that's where the curve can't cross, right? So that's like the off-limits number. So in this problem, where would the off-limits number be? At x equals 1. Because if you put 1 in here, you're going to get a 0 in the bottom, right? And you're not allowed to have a 0 in the bottom, so we have an asymptote there to block it. See how it makes sense? All right, what about the next one? Remember, vertical asymptotes only involve the denominator. I need to know where to put my vertical asymptote. Vertical asymptotes go wherever the denominator would be 0, because that's the off-limits number. So what would make that off-limits? Not 5, watch it, 5/3. So you have a vertical asymptote at x equals 5/3. I expect to see on your picture a dashed vertical line and a label up here that tells me where it is. A dashed vertical line and a label. That's all you do. Now, we're going to add to it, but we're taking it a step at a time. All right. Now take a look at that one. I heard somebody say it. Yeah, we're gonna have 2 of them down there now, because our denominator is x plus 2, x minus 2. Aren't there 2 off-limits numbers now, you guys?
Yeah.
The 2 off-limits numbers are x equals 2 and x equals -2. So when I draw my picture, I'm going to have a vertical asymptote at x equals -2 and a vertical asymptote at x equals 2. Remember, vertical asymptotes are whatever would make this 0. So you could say, what makes this 0? X squared equals 4, x equals plus or minus 2. So you had 2 asymptotes, 1 at 2, 1 at -2. Yes, ma'am.
So the numerator doesn't matter at
Nope. Now, the numerator will matter with horizontal asymptotes, but not with vertical ones, okay? So right now, all of these problems have to do with vertical, so we're just focused on denominator. All right, we're going to get through at least one or two more problems. I hope I see you on Tuesday. When we come back, I hope it's not the day off for you. I hope we have this period on Tuesday. I never can remember what periods I have when.
To remember it easier, it's like the last two periods of each day you don't have those.
So you're assuming that I remember what were the last two periods yesterday. My memory's not very good. All right, what do you think we're going to do here? We're going to plot vertical asymptotes. This is problem D. I've now moved on to page 9. What am I going to do to figure out where my asymptotes are? I'm going to factor. Only the bottom. That's all that factors anyway, but I'm going to go ahead and factor it. Where are you going to put those vertical asymptotes then? You're going to put one of them at -1, and you're going to label it x equals -1. And then you're going to put another one at 5 and label it x equals 5. One more, and this one's going to blow your mind. Let's see if you can figure out this is a good way to end with a blown mind. All right, tell me.
5 -1.
How do we want to start? Okay, we're going to factor. And we're going to factor everything, kids, because something crazy is going to happen.
Whoa, I don't think we're ready.
Whoa. I think you're ready. What is going to happen? I factored my top and I factored my bottom. We can cancel. Oh man. Now, I thought there might be 2 vertical asymptotes, but it turned out there is only 1. So I am going to put a vertical asymptote at the point, I'm just going to erase this guy because he's in the way. I'm going to put a vertical asymptote at -5.
Yes.
Now, Gabby, you are in charge. The next time we have class, you must remind me that we have to pick up on this problem because we're not done with it. Okay?
Is the top one horizontal?
We're going to get a horizontal asymptote, and actually, no, in this case it's 1, not -1. Yes, ma'am.
For problem C, go back to C, why did we factor on the top?
Because the
Yep.
top doesn't
Wait.
factor. It's x
Yep.
squared plus 1, and that doesn't factor. If it did factor, we would have.
If it was x minus
Got
1.
another good class to get to here.
Yep. All right. Oh wait, time out. Stop. Stop getting your watch.
Friday. It's Friday, guys. Friday. Can't leave without a hug.
I can't wait till she was going to stop recording.